Welcome friends to my YouTube channel Sommo Physics. Now in my last lecture I have told about the basic differences between Joule-Thomson process and adiabatic expansion, and also uh, I told the significance of Joule-Thomson coefficient. Now in my this lecture I shall going to discuss the adiabatic demagnetization process, and I already told that this is one of the powerful method of producing very low temperature. Okay, so let's proceed. So our topic is adiabatic demagnetization. Demagnetization. Okay, now what is the basic principle of this process? Now basically here we will take the example of a paramagnetic substance. Okay, here we deal with paramagnetic salt. Okay, now we all know that the atoms of a paramagnetic substance looks like teeny dipoles. Okay, they behave like teeny dipoles, and in the absence of external magnetic field, the dipoles are randomly oriented. The dipoles are randomly oriented. Okay, as a result, net dipole moment mu is 0. Okay, in the absence of external magnetic field, the dipoles are randomly oriented. As a result, net dipole moment is 0. But when an external magnetic field is applied, the dipoles tend to align in the direction of the field. Okay, say this is a dipole and this is the field direction. Now in the presence of external magnetic field, the dipole tend to align in the direction of the field, and this alignment of the dipoles depends upon two factors. One is dipole temperature and another is strength of the field. Strength of the field. Okay, so when a field is applied, the dipoles align in the direction of the field. Okay, now this alignment depends upon two factors, dipole temperature and strength of the field. Okay, now if we suddenly remove the field, then what happens? The dipoles will tend to bring to their original condition. Okay, if we remove the field, the dipoles will tend to bring to their original condition. Okay, so some work is to be done by them, and since the process is adiabatic, so no heat enters or leaves the system. So from which this work can be done? This work can be done at the expense of own internal energy of the dipoles. As a result, internal energy decreases and the temperature of the dipole decreases. Okay, so this is the basic principle. Okay, in the absence of external magnetic field, the dipoles are randomly oriented, so net dipole moment is 0. But when a field is applied, the dipoles tend to align in the direction of the field, and say this alignment depends upon two factors. One is the temperature of the dipole and another is the strength of the field. Now if the magnetic field is suddenly switched off, then the dipoles will tend to bring to their original condition. Okay, so removal of field, removal of B causes the dipoles to bring to their original position. Okay, so some work is to be done by them. Some work is to be done by them, and since the process is adiabatic, no heat enters or leaves the system, so work can only be done at the expense of own internal energy of the dipoles. Okay, So here work is to be done at the expense of own internal energy of the dipoles, because the process is adiabatic. Okay, for this reason temperature of the dipoles falls down. For this reason temperature of the dipoles fall down. Okay, so this is the principle of this process, adiabatic demagnetization process. Now our next task is to find out the amount of cooling produced in this expression. Okay, so let's do it. Dear guys, if you don't subscribe my channel, then kindly subscribe it to get latest videos on physics. Okay, and also share it to your friends. Okay, now what is the theory behind it? Now we all know that the state of a paramagnetic substance is determined by two quantities. One is magnetic moment and another is temperature. Okay, for paramagnetic substances these are the thermodynamic variables. So what will be the second TDS equation? We get TDS, this equals to CBDT minus T into del M del T B constant dB. Where what is CB? CB represents the specific heat at constant magnetic field. Specific heat at constant magnetic field. Okay, so this is the second TDS equation for a paramagnetic substance. Now we all know that paramagnetic substance obey Curie's law, that is M equals to some constant into B by T. So obviously del M del T B constant is negative, that means minus KB by T square. So paramagnetic substance obeys Curie's law, that is intensity of magnetization is inversely proportional to the absolute temperature. So del M del T B constant is minus KB by T square. Okay, so this is negative. So if this quantity is negative, then we can give a plus sign here because this is negative. So CBDT plus T del M del T B constant into dB. So we can write this. Okay, and since the process is adiabatic, entropy remains constant, so ds is 0. So the ultimate equation becomes this: CBDT plus T into del M del T B constant dB equal to 0. So this is the ultimate equation. Okay, now as I told earlier that paramagnetic substance obey Curie's law. So M, this is equals to KB by T. So what will be my del M del T B constant? This is simply minus KB upon T square. So this is what CBDT, this will be minus T into KB upon T square dB. This is equal to 0. We can write it. So more commonly what we write, CBDT, this is equals to KBdB by T. So if we rearrange this, we can write TDT, this simply K by CB B dB. If we rearrange this, we can write this equation. Okay, now we have to integrate this within the limits. Initial temperature say Ti, final temperature say Tf. TDT, and here say initial magnetic field you say BI and final magnetic field say BF. So that will be this. Okay, so we have to integrate this within the initial and final limits. So what we get, this is simply half, this is simply TF square minus TI square, this is simply K by 2CB, this is simply this. Fine, 2 cancels. Now what we usually do, this is demagnetization process. So after applying the magnetic field, later we have to remove it. So the final magnetic field should be removed. So here you can impose a condition that final magnetic field is now removed. So if we can make the final magnetic field 0. Fine, since the final magnetic field is removed. So let's see what does the equation becomes. Okay, so this TF square minus TI square can be written as TF plus TI, and this is TF minus TI, and if we put these zeros, this becomes minus KBI square by CB. Okay, so what will be my TF minus TI? This simply minus KBI square by CB, and that is simply TF plus TI. So we can write is by 2, this is 2. So this is delta T, this is minus KBI square by 2CB, this is called T average. So what is T average? Average temperature of the specimen, that is TF plus TI by 2. Average temperature of the paramagnetic salt or specimen, you can say. Okay, so thus we see that there is a minus sign. That means this amount of cooling is produced in adiabatic demagnetization process. So this negative sign indicates that the temperature of the salt or the substance or the specimen, whatever you can say, decreases. So this is the amount of cooling produced in adiabatic demagnetization. Okay, so this is the amount of cooling produced during adiabatic magnetization process. So you can find this in all books. You can follow A.B. Gupta book, Brijlal's book, or C.L. Aurora part 2. Okay, you will get this thing. So whenever you are asked to find out this expression, at first you have to write shortly the principle of this process, and then you have to find out the amount of cooling produced during adiabatic demagnetization. Okay, so this is what about adiabatic demagnetization. Okay, now one thing here, I have derived the expression of Joule-Thomson coefficient by using the enthalpy, or by using the porous plug experiment conditions. Okay, by taking that it is an isoenthalpic process, and there I derived the expression of JT coefficient by using the concept of constant enthalpy. Okay, now JT coefficient can also be expressed by using Maxwell's relation. Okay, how? We can write enthalpy as a function of enthalpy equals to this U plus PV. So what will be dH? Simply du plus PdV plus VdP. So since JT process is isoenthalpy, this is 0. So this can be written as TdS plus VdP. Okay. Now take entropy as a function of pressure and temperature. Okay. So since ds is a perfect differential, ds del s del p t dp plus del s del t p dt. Okay. Now substitute this value in equation 1. What you get? T del s, that means T del s del p temperature constant dp plus T del s del t pressure constant dt plus v dp equal to 0. Now from Maxwell's relation, this can be written as minus del v del t pressure constant, and this is simply Cp. So Cp dt plus v dp equal to 0. So this is simply what? Cp dt, this is equals to T into del v del t pressure constant minus v into dp. Now what would be my dt dp? My dt dp will be Jt coefficient, that is mu. This is simply 1 upon Cp T del v del t pressure constant minus v dp. So you can also find out Jt coefficient by using Maxwell's relation. Okay, so this is the result. Okay, so in today's lecture I shall discuss about the adiabatic demagnetization process and then alternative way to find out the Jt coefficient. Okay, now in our next class I shall going to discuss the few other important issues of this chapter, say properties of liquid helium, that I will discuss in next class. Okay, so dear guys, this is what up to today. Now kindly subscribe my channel to get latest videos on physics. Okay, thank you.